Physics 3030, the universe. This is lecture 12, and today our main topic will be dark matter. And here's a quick outline of what we're going to talk about here. Galaxy clusters and galactic rotation curves are some of the first pieces of evidence we had that there was some sort of missing matter. And then we'll talk about dark matter in that context. And then we'll talk about different ideas for what we think dark matter is. This is a really interesting topic because we don't know exactly what dark matter is. Now, this is sort of a little bit of a historical perspective, okay? Because the term dark matter didn't come around until much after these two gentlemen, these two astronomers that I'm about to talk about, okay? And in the 1930s, a Dutch astronomer named Jan Oort, so this is 1930s, observed that there was 3 times more gravitational attraction in the Milky Way. So this is a local effect in the Milky Way than predicted by Newtonian gravity. And he's just I'll sort of explain both of these in the same context because they really do mean the same thing. And then the other observation from a pretty early standpoint was Fritz Zwicky. And Zwicky was looking at a galaxy cluster called the Coma Cluster. And that's of galaxies. And he basically was observing something very similar, and that was that it seemed like there needed to be more mass to keep all of the galaxies together than was seen. So keep everything together. Then seemed like there needed to be more mass to keep everything together than seen. Okay, and this is a pretty surprising thing, right? In both of these measurements, the idea was that it was saying that the Milky Way, there was more gravitational attraction. So it seemed like there was more attraction due to gravity than there was stuff in the galaxy. And Fritz Zwicky was sort of saying the contrary to that, or the sort of opposite end of that, which was that there needed to be more mass to keep everything together than was seen. And these galaxies were moving far apart from each other, or moving away from each other and moving around each other, but they were staying in a cluster. And they had been in that cluster for a long time, but there didn't seem to be enough stuff to keep them together. Okay, and this is both of these ideas. Okay, really relate this idea that there's a interplay between gravitational potential energy, okay, which we've sort of talked about a little bit, and kinetic energy. And gravitational potential energy is just the energy you have from the force of gravity. Okay, so if I lift a cup up in the air and I just set it and I just let go of it, I've given it energy by lifting it up, right? Because now it can fall, and when it falls, the gravitational potential energy is converted by the force of gravity into kinetic energy, right? Where kinetic energy means the energy due to motion. Okay, and there's sort of just an interplay between these two types of energy. You're changing one for the other, and the idea behind all of these observations that was really peculiar, okay, is that for a given kinetic energy, you need some amount of gravitational energy to keep everything together. Okay, this hopefully makes some intuitive sense, right? If everything's moving really, really fast, then you need a larger amount of gravitational energy to keep it all from flying apart, right? Okay, and if everything is moving slower, it takes a little bit less amount of gravitational potential energy. And that's what Zwicky was seeing here, was that all of these galaxies were moving around, and he's using redshift and blue shift of the galaxies to see how fast they're moving. And it seemed like they were moving too fast to be bound together for how much stuff he could see. Okay. And this idea was sort of passed over. Okay. These gentlemen made these observations, and no one could come up with a very good idea of why that was the case. Okay. And then this woman, Vera Rubin, came along, and her graduate students made a bunch of painstaking observations of galaxy rotation curves, so galactic rotation curves, right? So the idea is that I have some galaxy, okay, maybe has some arms with it like this, okay, and some of these, so if I'm looking straight on from the top of this galaxy, it's really hard to tell how fast things are moving. But if I'm looking at it on the edge, so all I can see is sort of the bulge in the middle and on the edge here, right? If the thing is spinning, so, you know, let's say this one is spinning in this direction, so this one is sort of going, it's hard to draw this, into the board, and this side's coming out of the board, okay? Well, the side that's going into the board is moving away from us, so that's actually red-shifted because it is moving away from us. Remember these terms. And the other side is blue-shifted, just as I wrote it there. Okay, and so you can make detailed observations. If I make a detailed observation here of this arm, the stars in this arm, they should be a little bit red-shifted. And if I make a detailed observation of stars in this arm, they should be a little bit blue shifted. And I should be able to make observations all the way along the arm and out even into the outliers that are stars out kind of sitting outside. And I should be able to do that on this side as well, and do those red shifts and blue shifts and see how fast the galaxy is rotating. Now, as I said before, there's this relationship between gravitational energy and kinetic energy, okay? And there's a number of theorems in physics that tell us how much, on average, the gravitational energy should be for a certain amount of kinetic energy. And really, what this ends up looking like is because kinetic energy has to do with motion, right? What it is that, let's see, how should I say this? So the gravitational energy is dependent on 1 over r squared. We've talked about this a lot, actually, 1 over r. So this is a sort of dependent on radius. So you see radius over here, okay? And on the other side, the kinetic energy is really about velocity. So what the theorems of physics tell us is that it gives us the velocity as a function of radius. Okay, I should be able to put in a radius, and it tells me what the velocity is. Okay, so you graph these things, and you sort of look and see what it's supposed to be. And if we look at this galactic rotation curve over here, this is for M33 galaxy. The dotted line down here is a plot of that function of f, or of the velocity as a function of the radius. That's what Newtonian gravity predicts. Now, this is a very important point for the matter that's seen in the galaxy, right? So I see a certain amount of matter in the galaxy. It drops off, right? There's more in the bulge than there is in the arms, and this sort of dot plot over here is sort of what the M33 galaxy sort of looks like, and I plot that as a function, and it should be this red line. However, when Vera Rubin and her students did these rotation curves and looked, they got this line, and these yellow dots that I'm now making, sort of trying to make blue, are their observation points. Okay, and so they're sort of fit to this line, this light blue line, or light blue greenish line, and this line sort of points at the fact that there seems to be missing matter. Okay, and the reason for that is this is a much higher, see on this side over here is the velocity, right? So these blue dotted lines are a much higher velocity than you would expect. And if there wasn't more matter, so more gravitational force to keep everything together, everything would just fly apart with these velocities. So there had better be, and this is the first thought, right? There better be more mass to keep everything together. Okay, and so this is sort of where the idea of dark matter was born. And one of the big things is that Vera Rubin did so many observations with her students to show that this was not just one rotation curve. This was many different rotation curves. You can do this on different telescopes, and people independently corroborated this. And this is why the idea of dark matter took off really with Vera, as opposed to back in the 30s with Zwicky and Oort, because they only made a couple observations and sort of weren't sure what was going on. Okay? Okay. So now, after these observations were made, people looked for other proof of dark matter, and there happens to be sort of a great deal of things that point to dark matter. And one of the other really interesting ones is this idea of Einstein rings. Okay, we talked a little bit about Einstein rings when we talked about general relativity last week. And Einstein rings are when you have, remember, you've got, so this is sort of a top view. You have some massive body, right? You have some star in the background, and this is us here at Earth. Okay, and the star's light sort of radiates off the normal way it would, but this gravitational body in the center lenses this, okay, and so you get light bent back around, and when it comes back to us on Earth, it looks like, so this is a one-dimensional cut of this, but it looks like a ring all the way around this massive body. And so that's what we've got up here. You can see these blue sort of smudges on the end make up part of some rings of galaxies in the background, light in the background that's getting lensed by this galaxy in the middle. Okay, and GR, so general relativity, tells us what the mass has to be. The mass of the lens, right, of whatever it is in the center that is lensing the light. Okay, and when you calculate, you know how far away these things are in the background, and you calculate this, and it turns out that there's mass missing. Again, you know how much, and the idea here is that I know how much stuff is sort of in this galaxy because it's lit up. Or at least that's it should be your first approximation, right? And we're not just talking about stars. There's stars, but there's also gas, interstellar gas, and there's tons of mass in that gas. And we've taken that into account, right? We know that the gas gives off light in different parts of the spectra than the stars do, and we can tell how much there is. We can make pretty good estimates, right? And there still turns out to be mass missing. Okay, so that's the really neat thing. And so we do this over and over again, and we find that there's a certain amount of mass missing, and it is a huge amount of mass, right? So I've sort of left this out, but it's something on the order of, let's see, what would this be? It's about 6 times, something like that. 6 times the seen mass. So that deserves an exclamation point, right? So about 6 times the amount that we see is missing to account for the mass that should be in this calculation, where general relativity tells us how much mass is in the center. Crazy, crazy, tons of it. Okay, and so this is another sort of thing that points towards there being this some amount of mass that's missing. Then the other sort of proof, this is done in a slightly different way, and again, proof is a funny word, right? We never really think we can prove anything 100% in science, but we certainly have lots and lots of data to point to different things. And the idea of this one is if I look at the large-scale structure of the universe, right? So this sort of looks like a set of neurons or whatever, but this is actually a picture of galaxies along some sort of cosmic web. Okay, and if I look at models of the universe, so let's see. So astrophysicists will model the evolution of the universe, okay? Knowing what we know about physics, all of that stuff we talked about the early universe in a few lectures ago. And it turns out, so you take all of that stuff that we know, and if you try, you put it in there, you put all of that in as the initial data way back at the Big Bang, and if you don't include dark matter, then the crazy thing is, I'm going to call dark matter DM. If you don't include dark matter, you don't get today's structures. Okay, so what this is saying is we can't go back and, we can't do the experiment of building a whole new universe from scratch, right? But we can do it in the computer. And so we model the structure of the universe using a computer with what we think we started with. And if you don't put in the right amount of dark matter, the right percentage of dark matter, which is what it's predicted to be through the Einstein Rings and through the galactic rotation curves, you don't get the filamentous structure of the universe. You also don't get star formation in quite the same way. So star formation is affected, okay? And this is talking about now those population 3 stars, right? That they need a huge amount of mass to get started, and the dark matter helps to concentrate that mass in one place, okay? So this is sort of a neat idea. So we do the experiment in our computers, and it turns out that, oh my goodness, we don't have enough stuff to get the structures that we see without this dark matter. So these are all different ways that point at something that's missing out there. And just to give you an idea of what we're looking at, here's a little diagram of how much dark matter we really think there is, right? In the center here is the luminous matter. So that's like the bulge of the galaxy, and these are the arms of the galaxy. That's what we can see of a galaxy. And it looks like there's got to be a huge, what we call halo of dark matter around this thing, okay? And this is mostly from the galactic rotation curves, right? We look around at, there are still little stars, a number of stars out here, and you can look at how fast they're moving, and it looks like there's this sort of continuous big sphere of dark matter all around a galaxy. And so this is sort of what we look like, and this is what it looks like, and this is what's called the halo. So there's this big halo of dark matter sort of surrounding every galaxy. Okay, so the question is, what is this stuff? And your book talks a lot about the different types of what dark matter are, and we're just going to touch on some of them. So I like these funny things that I found on the internet. This is actually a real vitamin supplement. Okay, but what is this stuff? What are we looking at here? So when I say dark matter, a lot of you probably think of something that also implies dark in the name, which we talked about last time, which is black holes. So the question we're dealing with here is, what is dark matter? And let's think about some of the big things it could be, right? So they're not only black holes, right? We can't see black holes, so maybe there's just a ton of black holes surrounding everything. There's also white dwarfs, which are really hard to see stars, and neutron stars. Okay, and we talked a lot about black holes in the general relativity lecture, and I sort of wanted to do that before I started talking about dark matter, because this is sort of one of the obvious first guesses of what could be out there. And since these are all massive objects, and they're sort of big objects, okay, and the astrophysics community has a name for all of these things. They are massive, compact. Compact means like an aggregate of things, right? In this case, halo objects. So we're thinking about things sort of sitting in halo, and of course, for their love of acronyms, this is MACHO. So these are machos, okay, these big things. And we can do this test. And the idea is, if I have some galaxy, okay, and it's rotating, and there are black holes or any of these other objects sort of in the halo like this, right? If we're on an arm, so we're sitting here on the arm of the galaxy, and we see, you know, there's some black hole we can't really see, well, there are still stars behind it. And if we get in the line of sight, right, then the light from this star should be bent around that massive object as it comes to us at Earth. And so we should see lensing from these things. Okay. And the idea would be that, okay, if there's some black holes out there, there has to be a certain number of black holes, right? There better be a certain number of them, which is about 6 times the mass of what we can see, hiding out here. And if I know how many of them there should be, then I have some statistics about how often I should see Einstein rings like this. Okay. And it turns out that, you know, there are some out there, but not enough. Okay. And there's been a number of experiments that do this. They look for this type of lensing. Okay. And this only accounts for maybe a 10th-ish of how many, of how much stuff we need to account for this dark matter. So yeah, there's black holes, white dwarfs, neutron stars that it's really hard to see the luminescence of them. And you can tell that they're there from this gravitational lensing, but there's just not anywhere near enough of them to account for all of this stuff. Okay. So now the search is on for what is most of this stuff. And if it's not a big, massive, compact halo object, maybe it's something small. So maybe it's a tiny black hole. That's an idea. Tiny black hole. But the problem with this is, remember we talked a little bit about Hawking radiation, right? And if you do the calculation for Hawking radiation, all of the black holes would have evaporated by now. If they were... So the only way that people could really think about how these were formed was in the Big Bang. Okay, the only place where you could have formed lots of little black holes like this, and they would have evaporated by now. And so this can't be the explanation for what these things are. And you wouldn't see lensing from tiny black holes, but they would have already evaporated due to Hawking radiation. Okay, so now we're still trying to figure out what these things are. Okay, and so there's another idea. So if it's not a big interacting object, and it's not a tiny black hole, maybe it's some sort of weakly interacting, And this is in the generic sense of the word weakly interacting, not the specific weak interaction, though that is one of the ways that they may interact. So weakly interacting massive particles, right? Instead of compact objects, we're talking about particles. And of course, there's an acronym for this. This is Wimps. So, Wimps. What are the ideas? There's many ideas for Wimps. Maybe there's something that's lots and lots and lots and lots of little tiny particles. That's the idea here, right? So it's lots of tiny particles. Okay, and as I was sort of hinting at before, maybe there is an actual weak interaction particle that could be responsible for these particles. And of course, we have one on the list, right? So first candidate is the neutrino. We've talked a lot about neutrinos when we were talking about particles. Okay, this is the neutrino really only acts through the weak interaction, the weak force only. Okay, and so maybe we haven't seen it because it's so weakly interacting, and this could possibly it. However, this is under the category of something called hot dark matter. Okay, and the distinction is that hot dark matter, basically, the particles are moving fast. Because neutrinos are so light, they can move pretty close to the speed of light. In fact, there are a number of experiments right now that shoot neutrinos basically at the speed of light to like 8 or 9 digits. And they're not going exactly the speed of light, just a skosh below. And then there was an experiment a little while ago where they thought they were going faster. I mean, that's how close they're going, right? They're going pretty close to the speed of light. They're moving really fast. And it turns out that if I do the simulations, one of the specific ways, so if I do the simulations of structure, these can't form the sort of cosmic web structure that we see today. Okay, and so it probably is in neutrinos, but it's still out there. There could be some way it was neutrinos. And then there's a number of other different candidates, and I'm not going to go into tons of details here, but there's something called SUSY particles, and SUSY is short for super symmetry. Okay, and I'll leave you to sort of look up what supersymmetry is, but it actually is really important in string theory. And it basically says that every particle we see, every particle we see has a supersymmetric partner. And supersymmetric just means there's this some symmetry, just like we were talking about with all these different symmetries with particles before. There's some other partner that these particles have that we've never seen, and that's its supersymmetric partner. And we just haven't ever gotten to a high enough energy to see any of these. Okay, and actually the LHC is looking for these supersymmetric partners. And it said, well, if there's half of the particles in the world, if supersymmetry is correct, and half of the particles in the world are missing, then maybe some of those are out there, or not, and by missing I mean we've never actually seen them. Maybe they're sitting out there and they could act as these massive particles. So that's one idea. There's a third idea, which is these particles called axions. Axions. Okay, and these are theorized particles, which the SUSY particles are as well, that have to do with some invariance that's called CP invariance. And this is another particle theory, particle physics explanation. It's a predicted particle that has to do with this property of a lot of interactions. It's called CP invariance, which this is charge parity invariance. But the details we won't go into right here. But again, this is what theoretical physicists do, right? there's some measurement that we've taken, okay, and we don't have something to explain it. The one thing we know exists doesn't seem to explain it very well. So we used something that's cold dark matter. These are both under the heading of cold dark matter. And so we try and come up with possible explanations. Okay. And actually, the neat thing about both of these is that these explanations come from somewhere else. There's some other reason to look at these particles, and then oh, look, they might actually happen to be the dark matter that we're looking for. Okay. So I've sort of talked a lot about what this stuff could be if it's actually missing matter. Now, we call it dark matter because it's not luminous, and we don't know what it is. Okay. And so, and it makes up a huge amount of stuff out there, of all the stuff that's out there. There's there's another possibility besides it being something. So we've got the machos, which are big things, big missing mass. We have the wimps, which are small missing mass. But then there's another thing, another way that we could explain this, which is maybe there has to be a modification of gravity. And by gravity, I really mean general relativity. But on this scale, it really is looking at Newtonian mechanics. We're talking about huge. We're talking on a scale where the Newtonian mechanics often explain these things pretty well. Okay, and so there are different proponents for this. One is called MOND, which is modified Newtonian dynamics. Okay, that's sort of one possibility. And there are other possibilities as well. There's something called c² gravity. And this is, again, this is sort of where theoretical physicists live. Well, what's another way that we could explain this dark matter? Okay. And there is a explanation. There's something interesting. Work. Let's see if I can erase all this. There's an explanation. There's an experiment done, an observation done that I want to talk about. It's called the bullet cluster. Okay. And the idea here is that there's colliding galaxies. There are two galaxies that are colliding with each other. Okay. And, as this goes, most of the stuff in the galaxies doesn't hit each other, right? It just sort of passes through each other. And you can look at lensing. And the idea is that the dark matter doesn't move in the same way that the luminous matter moves. Okay, and what I mean here, right, is let's do a little bit of a diagram. Okay, so say I have a galaxy, and I'm going to draw it as dots because remember, it really is made out of tons of little dots. Okay, and then there's sort of a dark matter halo around the galaxy. Okay, and it's going to run into this blue galaxy over here. And it also has a dark matter halo. Okay, and they're moving at each other, right? So they're moving at each other like this. Okay, well, when they collide, we know that the luminous matter is really interactive. Okay, and so it will interact with itself. So I'll sort of move here. What's going to happen is, what you expect is the blue matter and the red matter to sort of be interacting with each other, okay? But the dark matter is sort of going to just keep moving. So I'll first draw the dark matter for the blue one. So if the blue one, what's going to happen is the blue galaxy will sort of get slowed down by this red stuff, the actual luminous matter. But the halo of dark matter should sort of keep moving, right? So it's centered over here. So let's draw this. So that's the luminous blue matter from that galaxy. And the dark matter will have moved over a little bit because the dark matter isn't sticking to the blue to the luminous matter because it's not very interactive, right? It doesn't have any way of interacting, so it'll sort of slip through everything. And then the same thing with the red. So I would expect to see a sort of distribution like this, where I'm going to draw, I only have 3 colors here, but I'm going to draw sort of, that's the red galaxy's dark matter, and that's the blue matter's dark matter. Okay, and so they're sort of shifted. The blue matter just keeps going through, the red matter keeps going through. And so the idea is I should be able to look at the lensing from this. So and when I look at the lensing from this, I should be able to see how these distributions change. Okay, and the idea is that this should happen if I'm looking at matter. So if this matter is moving through and it's not interacting, then I should get gravitational lensing in a distribution like this. So this is if dark matter's explanation is actually matter, then this should occur. And I can look at this by gravitational lensing. If, however, dark matter is a modification, then a modification of gravity, gravity, then it should not occur. And the reason for that is that it's a modification of the actual gravity of the luminous matter. So what we're saying is, well, there's not a dark matter halo. There's some other thing, some way of changing the equations that explains this. And as you can imagine, physicists would be much happier sort of to find a new particle. Remember that in the 60s and 70s and 80s, we were finding new particles all the time in particle accelerators. So the chance that dark matter is a new particle is a sort of much happier idea than that there's some complete modification of gravity. We don't want to change the whole theory. But, however, there are all kinds of things. We know that there's no theory of quantum gravity, so maybe a theory of quantum gravity would have dark matter pop out of it somehow. Now, this is not a quantum effect, it's some huge effect, but that's a possibility. Or maybe there's some modification that you need to do to gravity to make it quantizable, and once you do that, oh look, there's this explanation. It's not a new particle, it's just a change in the way that we look at gravity. So both sides of the coin are there, and most people really think that it's a particle that we haven't found, but it's sort of up to debate. That's the amazing thing about dark matter, is that it's this new idea, is this thing that's missing. It's like, it comes down to the idea that about 23% of the 23%, maybe a little more, of all the stuff in the universe is missing. Now, missing is a pretty anthropomorphic word in this case, right? Because it just means that we can't see it. It doesn't mean that it's actually missing. It's out there. We just, as humans sitting here on Earth, can't see it. So, but it's a crazy idea, right? There's this huge part we don't understand, and this is why it's so fun to be a theoretical physicist, and it's so fun to think about these things. And who knows? Maybe you guys you could have some idea of what this stuff is, and then we could go and test it. So, okay, this is a great topic, and I'm gonna end our discussion of dark matter here. Okay, thanks very much.